Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 12, Lunar, Lunacy. In the last lecture, we saw the scientific explanation for why the moon goes through its phases. In this lecture, we're going to look at some interesting aspects of the moon, and it's a variety of different things that we'll be examining. So the first one is, have you ever noticed that sometimes when you look up there at the moon, you can see the thin crescent moon, but you can also see the unlit side of the moon, or what should be the unlit side of the moon, but it seems to be lit up just a little bit. That unlit portion of the moon appears to glow because of reflected Earth light. That is Earth shine that is lighting up that side of the moon. Now, we call this sometimes earth shine. It's sometimes called ashen glow. My favorite one for it is the old moon in the new moon's arms, because you've got the new crescent moon right there, and you've got the old moon still shining through in the arms and the crescent arms of the new moon right there. So here's another photograph of it right next to the Pleiades, the little cluster of stars called the Seven Sisters. But there we go. There's the thin crescent moon, the waxing crescent right there, with the unlit side of the moon that appears to be lit up. Why do we only see this when the moon is a crescent? We don't usually see this when the moon is gibbous. And the answer to that goes back to our last lecture. Think about what happens when the moon is a waxing crescent. When the moon is a waxing crescent, an observer on Earth looking at the moon sees the moon mostly unlit with just a little bit lit up, right? The moon is just a thin waxing crescent. But what does the unlit side of the moon see? The unlit side of the moon, looking back at the Earth, sees a waning gibbous Earth. It sees an almost full Earth. When the moon is just a day or two past new, the unlit side of the moon is facing an almost full Earth, and all that Earth shine is what lights up the moon. But as the moon continues through its phases, by the time it gets to first quarter, it looks back at the Earth and it sees a third quarter of the Earth. The Earth is now only half lit up. And by the time the moon is a waxing gibbous and it looks back at the Earth, the Earth appears as a thin crescent in the sky. So the ashen glow, the old moon in the new moon's arms, is most strong right after a new moon, when we have a very thin crescent, because at that time, the Earth, as seen from the moon, appears fullest. The Earth is at its brightest. Okay? So that explains the ashen glow. All right. Learning catalytics. I want you to tell me what's wrong with this image. Okay? So there's an image right there. In learning catalytics, just type a couple words. This is a word cloud, so just type a few words. You don't have to type it in a complete sentence. Just tell me a couple words as to what's wrong with this image. All right. In my last lecture, I told you that one of my pet peeves was people drawing a crescent moon where the horns go beyond the halfway mark. That is, they wrap more than 180 degrees around the moon. Another pet peeve of mine, and this one I see a lot more often, is when people draw the moon and then they draw stars in the unlit portion of the moon. Now, remember what the moon is. The moon is a giant ball of rock that is a couple thousand miles across. Stars are much, you know now from lecture 1, that stars are much, much farther away than the moon. There are obviously no stars between us and the moon, because the moon is the closest celestial body to the Earth. Stars are enormous. They're the same size, and our sun is sort of a medium-sized star. The stars in the night sky are incredibly far away. They cannot shine through the solid rock moon. So this is clearly an artist's mistake, not realizing that the stars have to be behind the moon, and there's no way that the stars could shine through the moon. Now, I want to tell you a funny story about this. I didn't always use this image. For many, many years, I used this image to point this out to my class. I used the same learning catalytics question, but I used this image. To point out that the stars are shining through the moon. And then after class one day, a student came up to me and said, Mr. Murphy, I don't think those were stars. I think actually what's going on there, those are snowflakes, because if you look at the hills, they're covered in snow. And I think what they're pointing out there is not stars seen in the sky, but actually snowflakes falling. And as soon as they said that, I looked at that image and I said, oh my goodness, they're right. So I had to go out to the internet and find, and don't worry, you're easily able to find lots and lots of images that show the moon with stars in front of the crescent moon. So don't draw stars in front of the crescent moon. Now, another thing that I see all the time is a discussion of the names of the moon, especially the full moon, the names of the full moon. So let's talk a little bit about why there are names to the full moon. This is primarily something that comes from almanacs like the Farmer's Almanac, and it is a corruption of a Native American practice. So Native Americans did not have names to the month like we have names to the month. We have January, February, March, April, May, June, July, August. We have the names for the months. Native Americans didn't have names for the months like that, and they typically defined the month by what was going on during that month. And so the full moon of that month would get a name like the harvest moon, which occurs around the time of the harvest, or the hunter's moon in October, or the frost moon, the time of the first frost in November, or the cold moon in December, or the snow moon in January. They had these names that they used to describe the month in which the moon was going through its phases based on what was going on in the world around them today. Now, the almanacs have seemed to have made a very big deal about these, as if there's something much deeper going on behind these names than simply Native Americans naming the month based on what was going on around them. So that's where these come from. As I said, it's a corruption of an old Native American practice for naming the months, but those are just some of the common full moon names. Now, here's another interesting question. I want you to answer this one in learning catalytics. True or false? There is a noticeable increase in the number of human births during a full moon. So true or false? Go ahead, pause the lecture for a few seconds, go into learning catalytics and answer this question. All right, what did you put for this one? This is an absolutely fascinating question to me. And it's fascinating for a whole lot of reasons. But let's look at the scientific explanation. It is a common misconception that the moon affects our weather, the number of births, the number of arrests, the number of emergency room admissions, the number of psychiatric ward admissions. None of that is related to the phases of the moon. So let's talk about the number of births, because if you ask a doctor or a nurse that works in a hospital, particularly in the ward where babies are born, you will find that they will most likely tell you that yes, absolutely, there are more babies born during a full moon. Well, here's the thing. That is actually scientifically testable. So let's test it and find out. And an astronomer by the name of George Abell did exactly this. So he was an astronomer at the University of California, Los Angeles, and in the late 1970s, he looked at all the live births at the UCLA hospital between March of 1974 and April of 1978. Now, that was 4 years of data in a major metropolitan hospital. So there were 11,691 births during that time. And he found absolutely no correlation with the phase of the moon. Now, he realized people might argue that not all births are natural births today. Many of them are cesarean sections. And in that case, oftentimes the day and time of birth is determined by the medical team and not necessarily by nature. So he narrowed it down to just the 8,142 natural, not cesarean births, and still found no correlation with the phases of the moon. Dozens of studies have been done where astronomers have looked at the phases of the moon and birth rates, homicides, traffic accidents, assaults, suicides, disasters, psychiatric ward admissions. There has been no evidence that the phases of the moon affect any of these. And if you're interested, there's a great little book called The Outer Edge, Classic Investigations of the Paranormal, where scientists have explored some of these questions that are taken for truth. For example, the fact that there are more births during a full moon. And in particular, they have an article that explains this full moon misconception. So why do people believe this? If it's not true, and it is demonstrably not true, and by the way, I should point out, that doesn't mean the full moon doesn't affect things. There are absolutely animals on Earth who time the laying of eggs, for example, with respect to the phases of the moon. Turtles, or sea turtles, are a really good example of that. There are absolutely animals on Earth that time reproduction around the phases of the moon. But there's no evidence that it affects humans in that way. And so why does this happen? Why is it that really very, very well-educated nurses and doctors believe that there are more births during a full moon when it is demonstrably not true? And the answer to that is something that we all need to be careful of for the rest of our lives, and that is confirmation bias. Confirmation bias is something that everyone, whether you are a scientist or not, has to deal with. And confirmation bias is simply the fact that people are more likely to notice events that support a belief, and they'll tend to downplay or ignore discrepant events. People are more likely to remember positive instances and forget negative instances. Let me give you an example of this with respect to births and the phases of the moon. Imagine that you're a nurse that works in a hospital, and you work in the ward where babies are born. And you believe, or you have heard at least, you don't know for sure, but you have heard that there are more babies born during a full moon. And you have a really busy night at work. You go outside and there were lots and lots of babies born that night, and you go outside and you see a bright moon in the sky. Now, you're not going to check the calendar to make sure the moon was full that day. All it has to be is even close to full. In fact, I would argue it could be 3 days before full or 3 days after full, just so long as it looks like a big moon in the sky. It's going to confirm this thing that you heard, that there are more babies born during a full moon. And you'll say to yourself, yeah, that's why we had so many babies born tonight, because there was an almost full moon out there. Now, imagine what happens if you have a really quiet night. And you have a really quiet night and you go outside and you see a full moon in the sky. Now, what you should say to yourself is, oh, it's a quiet night, not many babies are born, but there's a full moon in the sky, so that disproves the fact. But that's not what you say to yourself. You say to yourself, oh, we got lucky tonight. It was a quiet night even though there was a full moon. You discount the evidence because subconsciously you are inclined to notice events that support a belief and downplay events, discrepant events that disprove a belief. It's the same kind of thing that if it's a really busy day and you go out and you see a thin crescent moon in the sky. Again, you should be able to say to yourself, oh, well, we had a really busy night. Lots of babies were born. It's a thin crescent moon. And so that proves that there are not more babies born during a full moon. But you're likely to come up with some other excuse. Oh, was there a power outage 9 months ago? Or maybe we just got unlucky and it was a really busy night. It's surprising how hard people work to confirm existing biases by distorting the events. And I think right now, all you have to do is look at talk radio, look at television, look at what's going on in the world around us, and you see that confirmation bias is rampant in the world today. There will be a news article about the president, and both sides will claim that that shows that what they've always thought about the president is true. You have to be very, very careful of confirmation bias, and that's especially true in science. In science, we have ways around this. The gold standard in science for getting around confirmation bias, especially in medicine, is called the double-blind study. And what the double-blind study is to make sure that you're not, imagine you're a physician and you are carrying out a clinical trial. You're testing a new medicine to see if it cures some disease. A double-blind test is designed so that your confirmation bias will play no role at all in whether the medicine is successful or not. The medicine will have to stand on its own. So here's how they do that. Of course, you don't tell the patients whether they're receiving the medicine or a placebo. The placebo effect is a very well-known effect that even if you treat a disease, even if you treat a problem that a patient is having with pills that are completely useless, sugar pills, for example, they will often tend to report an improvement in their symptoms or an improvement in their disease simply because they're being treated. So in order to get around the placebo effect, you'll typically divide your study into two halves. One half will receive the treatment, one half will receive the placebo, and you don't tell them which one they're receiving for obvious reasons. So people are taking these pills, but they don't know whether they're getting the medicine or they're getting the placebo. But here's the thing. You don't know either. You had a third party, another person, randomize the patients and randomize whether they would receive the placebo or whether they would receive the treatment, and you don't know which one the patient is receiving. And the reason for that is get around confirmation bias on your end. Because if you're a physician treating patients and you know that this patient's getting the medicine and that one's getting the placebo, you might treat them differently. So to get around confirmation bias, we do a double-blind study. Not only does the patient not know what they're receiving, but the doctor doesn't know which patients are getting the medicine and which patients are getting the placebo. Only a third party knows that. And only after the treatment is done and you look at the results, do you finally open the key that tells you which patients receive the treatment and which patients receive the placebo to determine whether the medicine was really effective or not. That is a standard way in science of getting around confirmation bias. We have many, many other ways of doing it. We have peer review where scientific results are reviewed by your peers, often by your competitors who very much would like to beat you to a discovery, and they will be some of your most critical opponents. And before your work sees the light of day in the publication in an outstanding journal, it will be peer reviewed to make sure that it stands up to scrutiny. So always be careful of confirmation bias. And I think this lunar lunacy, this idea that the phases of the moon affect these things, is a perfect example of exactly that. All right, let's move on to the next thing. Mark Twain said, "Everyone is a moon and has a dark side which he never shows to anybody." What did Mark Twain mean by that? Well, we know that the moon has a dark side. It's called the dark side of the moon. Pink Floyd made an excellent album called The Dark Side of the Moon. What is true about the dark side of the moon? I want you to take a few minutes and go to Learning Catalytics. So pause this video and go to Learning Catalytics and answer this question. The dark side of the moon, A, always faces away from the Earth but gets just as much light as the near side. B, always faces away from the Earth and gets no light. It's always dark. C, sometimes faces the Earth and gets just as much light as the near side. Or D, sometimes faces the Earth but gets no light, always dark. So go ahead and answer the question. All right, welcome back. So what's true in this case? Well, the answer that's true in this case is the far side of the moon is always facing away from the Earth, but it gets just as much light as the near side. And so A, always faces from the Earth, but gets just as much light as the near side, is the right answer to that one. Your answers may have been scrambled inside Learning Catalytics, but on this slide, it's the first one there. So let's talk about the rotation of the moon. The moon always keeps the same face towards the Earth. This is called the near side of the moon, and this is the side of the moon that you will see for your whole life. You will never in your life see the other side of the moon unless you are lucky enough to get in a spacecraft and be able to travel to the far side of the moon. In all of recorded human history so far, not many people have had the opportunity to do that. In fact, this is the near side of the moon. It's dominated by these dark patches called the Maria. We're going to find out later on in the semester. These are actually giant lava flows on the surface of the moon. If we look at the far side of the moon, the side facing away from the Earth, this is what it looks like. And this is a photograph, of course, that was taken by a spacecraft on the far side of the moon. There are still some Maria there, but not nearly as many. And the far side of the moon is dominated by craters. There's still lots and lots of craters on the near side. This particular photograph doesn't show them very well, but all this part of the moon down here is completely covered in craters, just like the far side is. But that's the difference between the near side and the far side. But like I said, the moon always keeps the same face towards the Earth. It always presents the same face. So a common misconception is that if the moon keeps the same face towards us, it must not rotate. But in fact, in order to keep the same face to us, it has to rotate. And let's see why that is. Imagine that the moon did not rotate. That means if the moon had a big tall mountain on it or an astronaut standing on it, as the moon went around the Earth like this, the astronaut would always be pointing in the same direction. The mountain would always be pointing in the same direction. So let's imagine the astronaut is standing here. They're facing in that direction. The moon orbits the Earth over here. Astronaut's facing in the same direction. The moon hasn't rotated at all. Astronaut's still facing in that direction. The moon hasn't rotated at all. Astronaut's still facing that way. The moon hasn't rotated, and they come back to where they started. But if we look at this for a second, when the Earth looks up at the moon, they see the side of the moon with the astronaut on it. Half an orbit later, the side with the astronaut on it is facing away from the Earth. Somebody on the Earth gets to see the whole moon in this case. That means that in order for the moon to keep the same face towards us, it must be rotating. And look what happens. Here's the truth of what's going on down at the bottom. Here's our astronaut right here. A quarter of an orbit later, the moon has rotated so that the astronaut is facing towards the Earth. Another quarter of an orbit later, the moon has done another quarter of a rotation so that the astronaut is now facing this way. Look, the astronaut used to be facing that way, and now half an orbit later, they're facing in the opposite direction. The moon has completed half of a rotation. And then, of course, another quarter of an orbit goes by, and the moon completes another quarter rotation. Another quarter of an orbit goes by, and the moon completes another quarter rotation. In order for the moon to keep the same face towards the Earth, it must be rotating. And it has to rotate at the same rate that it revolves. That means that in the 27.3 days that it takes the moon to orbit the Earth, the moon spins on its axis one time. That is, it spins every 27.3 days, which is the same rate of revolution around the Earth. Now you might wonder, wow, what an amazing coincidence that the orbit of the moon and the rotation of the moon are synchronized so that they're both exactly the same length. And here's the thing. It's actually quite common in our solar system. A lot of the moons of the planets are locked to their planets like this, and it comes from gravity, and in particular, it comes from tidal forces. Just like the moon raises tides on Earth, the Earth raises tides on the moon. Now, the moon doesn't have any liquid water that can slosh around, but the tides on the Earth squeeze and release the moon. And the moon has essentially settled so that the heavy part is facing towards the Earth. And the heavy part of the moon are actually all these giant lava flows. This lava that flowed out onto the surface, it's really very heavy and very, very dense. And so the moon has settled with the heavy face facing towards the Earth. And now, as it orbits the Earth, it always keeps that heavy face pointing towards the Earth. Io, Europa, Ganymede, the three of the inner moons of Jupiter, are tidally locked to the moon, to Jupiter. Other moons in the outer solar system of Saturn, Uranus, and Neptune are tidally locked to their parent planets. And even Pluto and its moon Charon are locked together. Pluto's moon always keeps the same face towards Pluto. But interestingly, its moon is so big and Pluto is so small that Pluto is tidally locked to its moon. Pluto and its moon constantly keep the same faces towards one another. If you lived on the side of Pluto opposite the moon, you would never even know that Pluto had a moon. Okay, so that's a little bit about the rotation and revolution. How about how much light does it get back there? The far side of the moon, I prefer calling it the far side of the moon because I think the dark side is a misnomer. It gets just as much light back there as the near side does. So I think a better name for it is not the dark side of the moon, but the far side. The dark side came from the fact that we just didn't know much about it. We didn't know what was on the far side of the moon, and because our knowledge of it was dark, it got the name the dark side of the moon. But like I said, I think a better name for it is the far side of the moon. As for how much sunlight it gets, well, that's pretty easy to figure out from this one right here. Think about what happens during a new moon. During a new moon, the side of the moon facing towards us, the near side is in darkness, the far side is fully lit up. So it's the opposite of a full moon right there. And so you can see that the far side of the moon is getting just as much light as the near side does during a full moon. And because the phases of the moon here are always opposite one another, ultimately you'll be able to see that it all balances out and the far side gets just as much light as the near side does. Okay. So that's the rotation of the moon. What about this? An astronaut standing on the near side of the moon would A, see the Earth rise once every 29.5 days and take nearly 15 days to cross the sky. B, see the Earth rise once every 27.3 days, the sidereal month, and take nearly 14 days to cross the sky. C, never see the Earth since it's never visible from the near side. Or D, always see the Earth in the same spot in the sky, never moving. Go ahead and think about the rotation of the moon here, and think about what an astronaut standing on the near side of the moon would see. Take about 15 seconds. Go ahead and answer the question. All right, welcome back. What's the answer to this one? It's fascinating. An astronaut standing on the surface of the moon. Because the moon rotates at the same rate that it revolves around the Earth, the moon always keeps the same face towards the Earth, but that means an astronaut on the Earth will always see the Earth in the same place in the lunar sky. Hopefully here in the next decade, we will see people returning to the surface of the moon, and when they do, I hope that one of the photographs that gets made is a long-term photograph that shows that for an astronaut standing on the moon, the Earth hangs up there in the sky. It never rises or sets. It just stays still up there in the sky. But what's interesting is sitting still there, it goes through its phases. Just like our moon goes through phases, the Earth will go through a full set of phases, but it won't ever rise or set. It'll just sit still up there in the sky. It'll make a fascinating movie. All right. So you might expect that if the Earth and the moon always keep the same face pointed towards one another, that we wouldn't get to see any more than 50% of the moon. However, if you make a movie of the moon going through its phases during the course of a month, you will see that the moon is rocking back and forth a little bit and it's nodding up and down a little bit. And those are just caused by some effects of the moon's orbit. The moon's orbit around the Earth is elliptical. Sometimes it's moving a little bit faster when it's close to the Earth. Sometimes it's moving a little bit slower when it's farther from the Earth. And over a long period of time, the moon's rotation and revolution have matched one another. However, for a short period of time, when the moon is closer to the Earth and moving a bit faster, we get to see around one side of the moon. And when the moon is farther from the Earth than average and moving slower, the rotation gets ahead of the moon and we get to see a little bit around the other side. And then sometimes the moon is a little bit below the Earth's orbit around the sun, so we get to peek over the pole and see a little bit over the top of the moon. And sometimes the moon is above the Earth's orbit around the sun, and we get to peek underneath and see a little bit of the bottom side of the moon. And we call this libration, this rocking of the moon back and forth. Now in this video, again, I apologize for how fast it's going. Ignore the moon going through its phases. What I want you to see is that the moon appears to be rocking back and forth. That rocking back and forth is called libration. And libration just means that we get to see a little bit more than half of the moon. Now, the little bit extra that we get to see is located way along the edges out here, and we don't get a very good view of it because we're not seeing it face on, we're seeing it edge on like that, so there's not much detail we can see. But altogether, we get to see about 59% of the moon is visible to us here on Earth. And fortunately, with spacecraft now, we've mapped the whole moon, near side and far side, so we know the moon quite well. But typically, you'll get to see about 59% of the moon. And this, like I said, this rocking is called libration. Another really cool movie is the one that's at the link down there at the bottom. This is a NASA video that they publish every year from the Goddard Space Flight Center that shows the moon every day of the year. It shows the phase of the moon. So you can see the dates here, the 8th of January, 9th, 10th, 11th, 12th, 13th of January, 14th, 15th, 16th, 17th, 18th. And what they're showing you here is not only the moon going through its phases, but you'll notice the libration, the moon rocking back and forth. You'll see that, look at Mare Crisium, the Sea of Crises here, and how it's moving both up and down as the moon moves from below the Earth's orbit to above the Earth's orbit, but it's also moving closer to the edge. I wouldn't say I'm better off than last year. It moves closer to the edge right there. It also shows you a little diagram up here showing you the moon going around the Earth with the sun off in a distant direction there. It shows you the distance from the Earth to the moon as the month goes on, at the times when the moon is a little bit closer than average and a little bit farther than average. Okay, just wanted to show that video. It's really cool. You can find this if you do Moon Phases 2020. Look for the one that's from the NASA Goddard Space Flight Center. Just watch that video. Okay. So why in the movie does the moon appear to be getting larger and smaller? So if you watch this video very carefully, you'll notice that the moon is getting a little bit bigger, smaller, bigger, smaller, bigger, smaller. So why is that? A, is the moon larger when it's rising and smaller when it's high overhead? B, is the moon's distance from the Earth varying during the month, or is it C, an optical illusion? Take about 10 seconds, answer this question on Learning Catalytics. Go ahead and pause this video while you pop over to Learning Catalytics. All right, welcome back. So what's the answer to this one? Well, the answer is B. The moon's distance from the Earth varies during a month. As the moon comes closer to us and farther away, when the moon is closer than average, it looks a little bit bigger. When it's farther than average, it looks a little bit smaller than average. Now, you've probably seen a rising moon, a moon that's just rising above the horizon, and it looks really big to you. And what's interesting about that is that's an optical illusion. So a lot of people have seen this rising moon looking really, really big. And then later on in the night, when the moon is much higher in the sky, it looks smaller. Turns out this is a really fascinating optical illusion. It has nothing to do with astronomy, because you can actually physically measure the size of the moon and measure the moon when it's high overhead. And you'll see that the moon is essentially the same size in both cases. And in fact, because if you think about where you are with relation to the moon, you're actually a little bit closer to it when it's high overhead. So it's actually a little bit bigger when it's high overhead than when it's down on the horizon. So why does it look so big when it's down on the horizon? Well, it turns out this optical effect is not very well understood. And that's because it doesn't have to do so much with astronomy. It has to do with how the human brain works and how the human brain perceives things. And that's incredibly complex. There's a great class that is taught over in the psychology of perception over in the psychology department that deals with a lot of these optical illusions and how you interpret things like this. So I put a couple articles here if you're interested in learning more about it. I'll give you the shortcut as to what we believe is going on. The first thing is, when a moon is rising up like this, you have lots of things in the foreground to compare it to. And you know some of the things in the foreground, like trees and houses and buildings, are really big. So your mind builds up this idea that the moon is really, really big. And then when it's high in the sky, you have nothing in the foreground to compare it to. So the moon looks really small to you. Another idea that's been put forth is that when people view the celestial sphere, they don't view it as an actual dome over their heads. They view the dome as being flattened, and they view the horizon as being farther away and the point overhead as being closer to them. And when they think of the sky in that way, the moon will look larger. Well, they'll think it looks larger when it's rising up than when it's high in the sky. As an example of the fact that this is an optical illusion, take a look at both these circles right here. There is a circle here on the horizon and a circle here. And I want you to compare the sizes of those two circles, and I want you to answer in your head, and we're not going to do this one in Learning Catalytics, which circle is larger, the one on the horizon or the one down at the bottom? Okay, now that was maybe a trick question. Let me ask this one. Which one appears larger? All right, when I look at the two of those, to me, it looks like this one is larger. The one here on the horizon looks larger than the one down here at the bottom. But if we very carefully measure both of them, we find out that both of them are in fact the same size. So it turns out the fact that this one looks bigger is just an optical illusion. And it has to do with all these things that are put here in perspective, making us think that this is very far away, very far off on the horizon, and therefore must be very big. But because this appears in front of all these things, it makes it look very close to us and very, very small. So even though the two circles are the same size, that one appears larger. Just know that for the rising moon is actually a little bit smaller than when the moon is high overhead. The fact that it appears larger is just an optical illusion. The last thing I want to talk about is the supermoon. Over the past couple years, I've noticed a trend in the media to declare supermoons a couple different times a year. So let's talk about what a supermoon is and what it is not. And I'll tell you what it is not right now. It is not a supermoon. So the first thing to know is as the moon orbits the Earth, its size varies as it gets closer to us and farther away from us. When the moon is closest to us, it looks a little bit bigger, and when it's farther away, it looks a little bit smaller. Now, the moon's orbit is elliptical enough that when the moon is closest to us, it's 5.5% closer than average, and when it's farthest from us, it's 5.5% farther than average. And a supermoon is officially defined as when the moon is full around the same time that it's at perigee, when it is closest to us. So perigee is when it's closer than average. Now, let's take a look at some pictures here. This is a picture of the moon when it is at its farthest from us, and this is a picture of the moon when it is at its closest to us. And yes, the moon is definitely bigger when it is closer, and it is definitely smaller when it is farther. But I have to say, if I covered up one half of this or covered up the other half of this, I probably wouldn't really notice that there's a significant difference in the size of the two moons. Here's another way to look at it. When the moon is at perigee there on the left, that's the moon at its largest, and there's the moon on the right when it is at apogee. To me, the word supermoon really means that the moon is super. And being 10% bigger than average, or I guess actually 11% bigger, so the moon is, when it's at its closest, it's 5.5% bigger than average, or it's about 11% bigger than when it is at its farthest. Being 11% bigger, that doesn't deserve the adjective super in front of it right there. I don't believe that the supermoon is super at all. And I think it's really quite crazy that we're doing this all the time. The media go out and they'll advertise that, oh, go out tonight and see the supermoon in the sky. The moon's going to be huge. And so people step outside and they look at the full moon, and I'll bet most of them look at it and say, yeah, it looks about the same size it does every month. It certainly doesn't look super to me. I think this is something that has been overplayed tremendously. And I'm afraid astronomers have fallen into this trap as well. Whenever I get asked for a radio interview about the supermoon, I'm always careful to point out that it's not actually that super. And then, interestingly, I've on a couple occasions, most often they're still interested. They think that's an interesting story, but on occasion, someone will say, "Well, then the story's not so interesting, and maybe it's not worth running at all." And it just goes to show you again that you have to be careful when you're consuming these things, that you really understand what we mean by the supermoon. So in any case, just know that when the moon is at its closest, around the time that the moon is full, the full moon will be a little bit bigger and a little bit brighter in the sky, but it will not be significantly bigger and it will not be significantly brighter. Okay. That ends our discussion of some interesting facts about the moon, just a couple different tidbits about the moon. So that ends lecture 12, Lunar Lunacy. Join me in our next lecture when we will begin our study of eclipses, and we will start with what are solar and lunar eclipses, and that will be in lecture 13.